Look at this chaotic city grid being constructed. Roads are misaligning, bridges lead nowhere, and structures are clipping right through each other. This physical mess perfectly visualizes the core problem of software engineering, the structural gap between what a creator intends to build and what actually gets built. For decades, we've tried to prevent this kind of digital chaos using the SDLC, or Software Development Lifecycle. Think of the SDLC as an intellectual contract. On one side, you have a product manager who understands the real-world problem. On the other, a human developer whose job is to translate that understanding into code. The vulnerability in that contract is human interpretation. A manager writes a specification, a developer reads it, and somewhere in that handoff, assumptions are made. The resulting codebase inevitably fills up with tiny translation errors that drift further and further from the original intent. In complex fields like geographic information systems, or GIS, which are frameworks for gathering, managing, and analyzing spatial data, that drift causes serious damage. If an urban planner simply asks a developer to show pedestrian data for a neighborhood, they are implicitly asking for a specific geometric data model and a complex spatial join. If the developer guesses the wrong mathematical model, the code runs perfectly, but the map lies to you. To fix this, a new approach called Spec-Driven Development, or SDD, replaces the human interpreter with an AI agent. Instead of the developer reading a passive document and guessing what it means, the AI agent is tightly constrained by executable rules that it must follow exactly. Under this system, specifications act as rigid laws rather than helpful suggestions. If the output fails, it means the instructions were wrong. The entire burden of accuracy shifts away from a coder's interpretation and lands squarely on the manager's ability to write explicit, watertight instructions. Geospatial applications offer the perfect testing ground for this AI-driven approach. Mapmaking involves high domain complexity, dealing with the curvature of the Earth and millions of data points, but surprisingly low technical ambiguity. That low ambiguity exists because modern mapmaking relies on strict open-source mathematical standards. An AI agent that has been trained on these standardized rules can execute them flawlessly, provided you give it the correct vocabulary to start with. This diagram illustrates the difference between human and machine instruction. On the left, a vague prompt like "show zones" on map results in a failure state. On the right, a structured input specifies the exact spatial reference identifier, SRID 3857, which is a specific code used to project the round Earth onto a flat screen, along with precise zoom levels. The AI takes that explicit math and successfully generates the geometry. By utilizing these precise open standards, teams can bypass the expensive commercial mapping platforms that historically dominated the industry. You no longer have to trap your data inside proprietary vendor ecosystems that charge you every time a user loads a map. Combining AI code generation with strict open standards ensures complete technical sovereignty. You own the data, you own the code, and you control the project's architecture for its entire lifespan. Here is the architectural stack that makes this sovereign system work, starting with the foundational base layer, the PostGIS database. PostGIS is an open-source extension that adds support for geographic objects to a standard relational database, making it the immovable bedrock for all the geographic math. Moving up the stack, we see data lines flowing directly from the database to form vector tiles. Vector tiles are square packets of geographic data that contain mathematical shapes rather than flat image pixels. Because the database handles this natively, it entirely removes the need to buy and maintain intermediary proprietary tile servers. Finally, a top visualization layer locks into place. Open-source rendering engines like MapLibre take those raw vector shapes and paint them with colors, adding the interactive panels and layouts that the user actually sees. To get an AI agent to build this stock accurately, we use a strict 3-tier scaffolding system. First, domain rules set the unbreakable architectural laws. Second, implementation plans break the project into numbered steps. Third, file templates provide raw code structure. This setup boxes the AI in, preventing it from hallucinating or deviating from the plan. By securing that database as the only permanently fixed piece of the architecture, the AI agent can safely swap, rewrite, or upgrade any of the upper layers, like switching out the front-end framework, without ever losing the core spatial integrity of your data. It is easy to assume this AI-driven paradigm eliminates the human developer, but the reality is much more interesting. The developer transitions from a manual bricklayer laying down lines of code to a master orchestrator directing the entire system. Their primary responsibility is now managing systemic complexity. An AI agent working in isolation cannot foresee how an asynchronous database query might collide with a map rendering on the user's screen. The human orchestrator has to anticipate and prevent those timeline collisions. The developer also acts as the ultimate semantic validator. An AI might write a line of code that is perfectly readable to the machine, but uses the wrong geometric projection for calculating the distance between two buildings. The developer is there to catch mathematical flaws that the AI thinks are correct. Under this workflow, the project's commit log, the historical record of all the changes made to the codebase, serves a totally new purpose. Instead of tracking human typos, it becomes a diagnostic tool. If you see a cluster of fixes on one map component, it highlights a logical flaw in the human-written instructions, not a bug in the code. The act of building complex geospatial software now relies entirely on writing precise, well-structured Markdown, which is just a lightweight text formatting language used to write plain text documents. When your instructions strictly govern how an AI builds the application, the specification itself becomes the code.